Okay, so today's class is not going to be long because this is our last topic. All right. So remember, previously I have mentioned that there are three types of PDE that we are going to discuss. The first one is heat equation, okay, and then wave equation and Laplace. And for wave equation, we can have an option of another method by using D'Alembert method, okay, where the equation itself must be for infinite boundaries. Only then we can use the D'Alembert. Okay, and then the rest of the PDE types for the chapter here, we are going to use MSV, method of separation of variables. All right, so as for now, this is Laplace equation. Okay, how can you know that this is Laplace equation? So Laplace equation involve del squared u over del x squared plus del squared u over del y squared equals to 0, right? Where the range of x is from 0 to a and y from 0 to b. So a and b somehow is given in terms of value and somehow is given in terms of constant, depends, right? Now, this is Laplace equation. As you can see, there is no time involved. Okay, we can see that there is no dependence on time. Okay, just on the spatial variables, just on x, y itself. So we have only x and y, where x and y can be anything, right? So this kind of function of Laplace equation here can be in terms of steady state equation, steady state situation for temperature, for stress, for potential distributions, right? Okay, so this Laplace doesn't involve with time. Okay, so it is another state. This is another form of steady state situation where if we solve this kind of Laplace, somehow we can find the steady state temperature, the steady state stress distribution, or the steady state potential distribution. So these are an example of the application use, right? Okay, so now, of course, by MSV, of course, we have to reduce the PDE to ODE. So you have del squared u del x squared plus del squared u del y squared. So the expected solution should involve with u in terms of x and y, where it is a combination, it is a production of x and y. So u xy equals to xy. So a function of x and a function of y. Okay, back to the PDE. So this is your PDE. This is your expected solution. Okay, mapping with these two, you have to have del squared u del x squared where it is u double x. You have to have del squared u del y squared where it is u double y. Just differentiate the expected solution, then substitute to the PDE. So you have this del squared u del x squared is u double x, which is x double y, x double prime y, plus with del squared u del y squared, which is u double y, which is xy double prime. Okay, and then just substitute. Okay, and then separate the variables. Okay, why we have to do this? Of course, we have to have the ODE. Okay, I think everyone has passed this level, right? By reducing the PDE to ODE, differentiate according to the PDE given, and then substitute to the PDE given, okay, and then simplify, and then separate, and then these two are equal when there exists a constant of lambda. So from here, we can separate the function of PDE now becomes ODE. Okay, are we clear?
Yes, Doctor.
All right, so now let's take a look at this example. All right, so today is our last lecture discussing the topics. So better you respond after this. We're just going to discuss about our next assignment. And if you have question, you can discuss also. All right, so now example 6, we have a square plate. We have a square plate bounded by x0, xa, y0, and y equals to a. So it is mentioned already, apply the Laplace. So this is Laplace to determine the potential distribution over the plate subject to the following conditions. So the conditions are given. So of course you have to reduce, same, right? Reduce to get this. Okay. Once you reduce, proceed to the next step where we have to have the boundary condition for ODE. So the given condition here is U0y. U0y means that x is 0. Where can we substitute this x? Substitute to the our expected solution. So when x is 0, okay, when x is 0, u equals to 0. So x 0, y equals to 0. So putting y to the right hand side will give you x0 equals to 0. So this is your first boundary condition. Okay? And then when x equals to a, so when x equals to a, just substitute a here. Then you have xa. When x equals to a, y equals to 0. So equals to 0. Okay, again, xa equals to 0. Okay, and we have another variable here, y. So just take this condition, ux 0 equals to 0 means when y equals to 0. When y equals to 0, ux 0 equals to 0, then we have y0 equals to 0. Okay. Right. Then let's save another condition for your initial condition later on. All right. Now, we have the ODE. We have the condition. And then our next step is, of course, to consider all cases. Okay. And the cases is always considering the expected solution. Okay. Now, we have this as our ODE. That is your ODE. Okay. So in order to consider all cases, same process with the previous examples, with the previous topics, with the previous types of PDE that we have discussed. Of course, we have to consider cases of lambda where lambda involved equals to 0, okay, greater than 0, and also less than 0. Okay, now when lambda equals to 0, then this PDE, okay, take a look at this PDE, then your PDE will be x double prime equals to 0. Change to characteristic equation will give you m1, m2 equals to 0. All right. So this is real and equal. Then this is the solution of x. Okay. Applying the condition, when x0 equals to 0, just substitute 0 here. Then a is 0. Okay. Then when a is 0, so the solution now becomes x equals to bx. And another solution, xa equals to 0, right? So just substitute x here with a. So xa equals to 0, ba equals to 0, which give you b equals to 0. When a is 0, b is 0, so this is 0, this is 0, then your x is 0. And remember, the solution should be a combination of x and y. Then when x is 0, no point to find y. So we just put no interest for this solution. So this is the first solution of case 1. Is that clear?
Yes, sir.
Okay. And then proceed with the second case. Okay, in our second case, the lambda should be greater than 0. So be it p squared. Okay. Then just substitute to the ODE. Characteristic equation give you m squared minus p squared will give you m equals to plus minus p. where this is real and distinct. Okay, so when it is real and distinct, then this is the solution, right? Now, by using this solution, apply the condition. When x0 equals to 0, will give you what? Just substitute x here with 0, so becomes a plus b equals to 0, will give you b equals to minus a. Okay, another one, just update the solution. When b equals to minus a, then we just can have our solution x equals to a e px minus e minus bx. So apply the second condition. Xa equals to 0. So x here equals to a now. Okay, so xa equals to 0. Alright, then putting this to the right hand side will give you a equals to 0 also. And a is 0, b equals to minus a will give you x is 0. Again, no interest. Alright, so this is your solution for second case. Okay, and then same process. Lambda now is less than 0, equals to negative p squared. Okay, so when it is negative p squared, substitute to, sorry, are you following me or am I too fast? Okay, right. So now when lambda less than 0, be it lambda is minus p squared. This is just the same process, but with the different equation. So usually when case 1, case 2 is 0, then the problem should be here, right? Okay, the problem should be here. We want to have the solution. And remember, when, okay, take note that when the answer is no interest mean trivial solution, there will be no mark given for the trivial solution. Just focus on the case of having the solution. Okay, so now case 3, lambda less than 0, lambda minus p squared. Substitute to the ODE here. Will give you the characteristic equation m squared plus p squared equals to 0. So solving this will give you complex root. Okay, m plus minus pi. So when it is a complex root, then this is the solution of x. Again, substitute the boundary condition. Use the condition given. X equals to 0, x equals to 0. X0 equals to 0, substitute here with 0 and 0 will give you a equals to 0. Okay, and then when a is 0, what's left? X equals to b sine px. Okay, now when x equals to b sine px, apply another condition. Xa equals to 0. Substitute a here. Okay, in your x. So you have b sine pa equals to 0. Okay, so if you are reaching to this expression, of course, we can just conclude b equals to 0, right? But for this case, b cannot be 0. Why? Because, why? Anyone has an idea? Why b cannot be 0 for this case? Trivial solution means there is no solution at all for all cases, right? Okay, thank you. So if b equals to 0, then there is no point solving this. You will have no solution. So we cannot have b equals to 0 then. We have to make sure that sine PA equals to 0. So technically, when sine PA equals to 0, and you know that sine and pi equals to 0, then you just can compare these two. Okay. Generally, you know that sine and pi equals to 0. Now, sine PA equals to 0, so PA equals to n pi, then P equals to n pi over E. So instead of finding this B, we can at least find the constant of P. Okay, so your P equals to n pi over A. Now, your x here, the solution of x here, now becomes x equals to b sine n pi x over a. So this is your x. When you have your x, then you need to find your y. All right? So y, substitute again. So this is your y double prime minus p squared y equals to 0. Change to the characteristic equation will give you real and distinct. So this is the solution for real and distinct. All right, again, we have the condition of y. Y 0 equals to 0. So substitute y equals to 0 here. So y equals to 0, substitute here. Then it is equals to 0. Then b equals to minus a. Okay. And when b equals to minus a, just substitute here. Then we can have y equals to ae py minus e minus py. Okay. Right. So now, what is your p? So just substitute your p is n pi over a. So this is your y. Now you have your x and you have your y. Okay. Then remember our expected solution should be uxy equals to xy. Just combine both. Okay. So you have your x, you have your y. Okay. Now this is your x, this is your y, this is your x, this is your y. Okay, why we put bn there? Anyone? Why we put bn there instead of only b here? We have b here. Okay, we put bn because we need to put some, because this n comes from a sequence. Okay, now x is b sine n pi x over a. So since we have n there, it should be xn. Since we have n there, it should be yn. So un equals to xn, yn. Alright? So this is bn, this is an, both are constant. Then we just can put another constant an, which is an equals to an times bn. We just simplify the expression. Alright? So in order to get uxy, and since here we have un, you just can combine everything. Then in order for you to omit that n, we just can put the summation there. Then we have uxy. Alright, uxy equals to u case 1, this is 0, u plus u case 2, this is 0 plus u case 3. So this is your case 3. Okay, any question up to this point? Everyone understand? Everything's good? Okay. So this is your u. Right? Now it's getting easier, right? Compared to the previous one, compared to the first time you did it. Right? So now you have your uxy. And remember, this is just only general solution. There are still a constant there. Okay? So that's why we have to use all the condition given. Okay. Now, looking at the initial condition given here. ux0 equals to 0, uxa equals to expression there. Okay. When we use ux0 equals to 0, means you substitute y with 0 here. This one, y with 0. Then we have, this is 1. This is 1 minus 1, 0. Then we cannot use this. Actually, why we cannot use this? Another reason is because we have used this condition previously. Okay, here, in here. Alright? But still, you have to check. Okay? Sometimes you can use it again. Okay, then the next condition given, uxa equals to u0 sine pi x. Okay, uxa equals to u0 sine pi x over a plus 2 sine 2 pi x. So this is based on the given condition. So this is given here. This is based on the given condition. Okay, now we want to substitute y with a there. Okay, y here with a. Okay, this is uxa equals to u0. So when you substitute y with a, here y with a, then we can have what? N pi a over a. That's why we have only n pi here. This is a negative n pi. So uxa, when y here is a, then again rewrite the expression summation an sine n pi x over a exponent n pi minus n pi equals to u0 sine pi x over a plus 2 sine pi x over a. So equals to this. So this is based on the condition. Okay, understand or not? What we are doing just now is substituting y with a. Okay, and then equal with the expression given here. Okay, everyone understand up to this point? Any question? All right. So now we want to solve this in order to identify what is our constant. Okay, so before this, usually in our last condition apply, the form is in terms of Fourier series, then we can compare, we can find the constant based on the Fourier series. Okay, it is not always like that. Of course, you need to compare, but for this case, there is no Fourier series involved here, all right? So there is no Fourier series involved, then you have to find the value of constant there manually. Okay, so how can we do this? All right, now this is summation an sine n pi x over a and times with exponent n pi minus exponent minus n pi. And remember, exponent n pi minus exponent minus n pi, if we divide by 2, then we can have sine n pi, right? Okay, so why we have to do this? It's not always like this. You can still use exponent, but this is just a simplification process. Okay, if you want to use exponent, then it is also doable, but we want to avoid some sort of complicated expression. Okay, so this is exponent n pi minus exponent minus n pi. But you know that exponent n pi minus exponent minus n pi over 2 is sine n pi. So if we want to substitute this sine, okay, we have to create another value of 2 in order to eliminate that 2. Understand or not? So if we check, okay, let's say if we check 2an sine n pi x over a times with sine is exponent n pi minus exponent minus n pi over 2. Now, if we eliminate these 2, we are going to have again our original expression. Okay, so now if you want to substitute this exponent n pi minus exponent minus n pi with sine, then you just put 2 here. Okay, because we don't want to change the expression. We just do some modification without changing the original expression. Okay, now this an now becomes 2an. Okay, then we just can simplify this 2an by using bn. So we can just create another constant of bn. Okay, so same process. Okay, same expression equals to, now this 2an is bn. Sine n pi x over a, sine n pi. So now it is simplified based on our sine n pi then. Okay, up to this point, any question? Okay, take a look first. If you have question, you can ask. Anyone has question? All good?
I think it's okay, Doctor.
Okay. Thank you for your response. Okay, now, as you can see, in order to find the constant, we need to do some comparison. All right. And as you can see from the left part, we have two expressions. And then for the right part, it is in terms of summation, then n equals to 1 up until infinity. So we don't want our expression of this summation to be up until infinity. So since we want to compare to the left-hand side, and left-hand side only has two expressions, then it is enough for you to expand the right expression up to only n equals to 2. Okay, so how? So now we have expression 1, we have expression 2. Then when n equals to 1, we have b1. N equals to 1, so sine pi x. N equals to 1, so sine pi. Okay, and then second expression, when n equals to 2, sine 2 pi x over a, and then sine 2 pi. Okay, of course, theoretically, we can expand up until infinity, b3, b4, b5, until b infinity, but we just want to compare to the left-hand side. Let's just stop until here. Okay, so now you can compare. As you can see, the first expression compare with the first expression, the second compare with the second expression. U naught sine pi x over a equals to b1 sine pi x over a sine pi. So this is sine pi x over a, this is sine pi x over a, then b1 is u naught over sine pi. Okay, and then b2. Okay, compare the left hand side and the right hand side, then you have sine 2 pi, sine 2 pi. Okay, then we just have sine 2 pi. B2 equals to 2u naught. Then B2 is 2u naught sine 2 pi. Okay, so remember why we have to apply the condition at the first place here, because we want to find all constant value in the general solution. So this is just your general solution. Okay, and then all the condition given is given. Why? Because we want to find the constant in order to obtain our particular solution. All right. So now you have your B1 and B2. Okay. And then just substitute. Remember, in your general solution, okay, in your general solution, we have uxy summation an. And remember, what is an? Remember, we have substitute bn with 2an. So 2an, an equals to bn over 2 again. Right, so from here. Now, an is bn over 2. Sine n pi x over a, exponent n pi y minus exponent minus n pi y over a. So substitute when n equals to 1, what is your b1? When n equals to 2, what is your b2? Okay, and then this is your final answer. Okay, and as you can see, you can what we call factorize, right? This expression. So uxy equals to sine n pi x, both u naught, okay, u naught sine n pi x over a exponent n pi y minus n pi y over a. So 1 over 2 plus 1. Right. So this is a simplified version of the final expression of the any question. Understand or not? Yes. Because the given condition is only up to 2 expression, then you just need to stop n equals to 2. Okay. This is just the idea of how we simplify the expression. And if you want to have general form of Bn, it is also doable, right? B1 and B2, then Bn equals to what? B1 u naught, B2 2 u naught, then Bn is n u naught sine n pi. Right, also can. But for this case, we just consider the condition given, which is up to 2 coefficient only. So we just stop up until B1 and B2. Okay, is that clear? How about the rest of you? From 1 to 10, where are you? We are reaching the final topic and final example today. One over 2 plus 1, 3 over 2, right? Or am I wrong? 1 over 2 plus 1. This one is 1 over 2 plus 1. Right, so becomes 3 over 2. This is, oh, okay. Sorry, 2 pi here. Then cannot. Then we cannot simplify this. Okay, thank you. So we just take the same expression outside. This is u naught. This is u naught sine pi sine 2 pi. Okay. So u naught we have here 1. Okay. Or if you want to leave it like this, it is enough already. All right. Okay, are we good?